All right, before we move on, let me give a brief review of the previous video. We looked at this diagram, the relationship between the different Fourier pairs, and talked about that. Now, most of the previous video was talking about this one example of a 10 function and turning a single 10 function at the origin into a periodic series of 10 functions and computing the Fourier transform of that. And of course, you can make a Fourier series of a single 10 function because it's on a finite interval. And we related the Fourier series to the Fourier transform. And the answer is that the Fourier series and the Fourier transform are very closely related. And the only difference is by using the frequencies where the Fourier series exists, and changing the values of the frequency coefficients to impulses, and then multiplying by 2 pi over t. And now, most of this was a derivation of that, using a sequence of delta functions. So we went to the sequence of delta functions, found the Fourier inverse transform of that by going through the Fourier series again relating Fourier series to Fourier transform, and finally got the result that we wanted. Now, I wrote here that slides 18 through 20 specialize to the case t equals 1. That's not true. So I'll just say this a recap. If we look at slides 18 through 20 and go here, so this is slide 19. So you can see here that he's just saying again the same sort of thing, that the impulses substitute for the Fourier coefficients, because when you integrate, the integral weight of each one of these pulses is 1, and you get pretty much the same thing. And here the frequency is explicit in the delta function. Here you don't have the frequency in the delta function, but because you're multiplying by a sub k, but a sub k multiplies a complex exponential that has the frequency in it. Right? So we just have this same sort of thing. And the relationship between the coefficients of the pulses and the values of ak is 2 pi over t. If I multiply this by 2 pi over t, I'm going to get, because t is 4. Sorry, you don't multiply by 2 pi over t, you simply multiply by 2 pi. Take this, multiply by 2 pi, you get these results. All right, if you can go back and look at the derivation, that's what we found. That's the relationship between the Fourier coefficient and the coefficient of the impulses. Right. So on to slide 21. Now I have some commentary on this. So here he shows what happens in the time space, and I put here what's happening in the frequency space. All right. So if he showed how to go from here to here, if you look at the original Fourier transform that he has back here, this is aperiodic and continuous in frequency. Right. So if you think about going backwards, this becomes aperiodic and discrete in frequency. So you're sampling at various frequencies. So if we think about going backwards, we're sampling in frequency. Okay. Now, the opposite of sampling is interpolate. You have samples, and you try to find the values in between. You use interpolation. Right? So if you look at this same relationship in the Fourier space, in the frequency space, that's what's happening to the Fourier transform when this is happening to the time signal. Right? Now, here's the next point. Moving horizontally in the time domain is like moving vertically in the frequency domain. Now, why is that? Look at this. Aperiodic, discrete in frequency. In the frequency space, that's the same thing as this signal in the time space. Here we're talking about aperiodic, discrete signals. So this is the same kind of signal in time that this signal is in the frequency space. Right? And here we have interpolate in frequency and sampling in frequency, just like we have down here, interpolate and sample. Okay, so that means that the frequency transform from here to here, the change in the frequency transform from here to here matches the change in the time transform here. So what does that mean? There's this symmetry between time and frequency. If the frequency change is just like the time change up here, sorry about my mouse, okay, the frequency change across is the same as the time change vertically, right? From here to here in frequency is like going from here to here in time. That means going from here to here in time is like going from here to here in frequency, right? So what that means is that this is going to have a periodic, continuous time frequency representation. Okay, and to go to here, we're going to have to do periodic extension, and t goes to, and in this case, frequency goes to infinity. So that's what I show. I believe I show that down here. All right, so the same thing you do with time up here, you can do with frequency up here, down in here. Right? So let me show one more relationship here. In slides 22 and 23, he shows the type of signal in time space and the type of signal in the corresponding signal in the frequency space. Now here it looks different because he's wrapping this around a circle. But wrapping around a circle, as I indicated in one of the earlier videos, wrapping around a circle just indicates that this is a periodic function, just like this one here. Okay, or just like this one here. Right. So, and then this one here is discrete with infinite extent. This here is discrete with infinite extent. This one here is continuous periodic. This one here is continuous periodic. Okay, so the fact that he wraps this around a circle is just convention. Really, this is exactly the same as what you have up here, and this is exactly the same as this. This is exactly the same as this. Right? So because there's this symmetry between time and frequency. Okay, well, let me stop here, and I will make another video to explain the homework assignment that relates to this. And all this material is very useful when looking at the homework assignment problems. Okay, thanks for watching.